Hello, this is Troy, and today we're going to be working on section 4.3 of Algebra 2, which is all about dividing polynomials. So there's two different methods to divide polynomials. The first one that we're going to go over is what we just call polynomial long division. And what we mean when we say we're dividing polynomials is that we can take any expression that looks like this. So we have x squared plus 3x plus 2 right here. And we have 2x to the fourth plus 3x to the third plus 5x minus 1. These are both polynomials, and we want to divide them, meaning we're doing yellow divided by blue here. So with long division, in order to kind of remind ourselves how we do long division just with integers usually, we'll just do a problem off to the side here, which is we'll do 256 divided by 7. So with long division, as we know, we first check does 7 go into 2? It does not. It goes into 25 3 times. So we write a 3 up here. 7 times 3 is 21. We subtract these. 25 minus 21 is 4. And we drop down to 6. So now we have 46 down here. And we're doing this process again. Now we're saying how many times does 7 go into 46? Well, 7 goes into 42 6 times. So now we have a 42 down here. We're subtracting again, and now we have a 4 right here. At this point, with integers, we sometimes keep going, but with polynomials, we don't have decimals, so instead we use remainders. So when we first learn long division, we usually just keep this as a remainder. Our remainder is 4, so we'd say remainder 4. Another way to write this quotient would be 36 remainder 4, or 36 and 4/7 because we have a remainder 4 of the divisor, which was 7. So 36 and 4/7. And so that's our remainder. And then here, what we can do is we can just write a plus right here because 36 plus 4/7 is therefore our entire solution there. So this is the format that we're eventually going to use with polynomials as well. So we'll see how it works now with polynomials. So we set it up the same way and use the same process here. So we're dividing this yellow one by the blue one. So the blue is going to be outside of our long division. Okay, 2x to the fourth plus 3x to the third. Now notice that there is no term that has a power of 2. It skips straight from 3 to just a power of 1 or no power there at all. However, it's going to be easier for us if we have our like a power of 2 in our division problem. So what we do is we just write that there's 0x squared here. Kind of like if you had an integer that had a 0 in one of its digits, like you would still write that 0 out. So we're writing plus 0x squared plus 5x is still there, and then minus 1. And then on the outside, we'll write x squared. On the outside, it doesn't matter so much about, in this case, it doesn't skip any terms, but if it did, we wouldn't have to necessarily use the 0x. So x squared plus 3x plus 2. And then with long division, if you don't use 0x, it's doable, but it lines up a lot better if you do include these extra zeros here. Okay, so first step of long division is we say how many times does this number go into, we first want to check sort of, here it was checking the first digit, here it's checking the first term. We want to check how many times does our divisor go into 2x to the fourth. Well, all we're really interested in here is how many times this biggest term goes in, because the other terms have lower degrees, and so therefore they automatically will go in enough times to 2x to the fourth. So really, the limiting factor here is going to be x squared. And so because x squared times another x squared would then give us x to the fourth, we know that we're going to have x squared, but there's also this 2 out front here. So I'm going to write here, I'm going to write 2x squared. Notice I'm writing it in line with the other x squared right here. I like to do that with polynomial long division because it keeps everything neat and organized. Um, and so what we can see now is that if we took 2x squared and multiplied it by this green x squared, we would get 2x to the fourth. So that's kind of the idea of how many times does x squared go into 2x to the fourth? We're just dividing 2x to the fourth by x squared. Now what we do is we take what we wrote up here and we multiply it out by the divisor outside here. So 2x squared times all of this now. We have to kind of distribute it to every term here. So 2x squared times x squared is 2x to the fourth. These should always cancel because that's kind of the idea here. And then we just keep distributing. So plus 6x cubed. Notice I'm still keeping everything lined up in terms of the exponent on x. And then plus 4x squared. So you can see now why it's useful to have that x squared because everything lines up. Cool. And then remember what we did up here is we then subtracted what we just wrote here. We subtracted it from what's above it. Now, because this is one big expression with pluses and sometimes minuses, we need to put parentheses like this to indicate that everything is being subtracted, not just that first term. So these ones should always cancel, so it's just 0, but we don't have to write that 0 here. But now we have 3x cubed minus 6x cubed. That gives us negative 3x cubed. And then 0x cubed minus 4x cubed is negative, or sorry, squared is negative 4x squared. And then we drop down the next digit, or in this case, we drop down the next term, which is going to be 5x. As long as you always just drop down a term, it should help you out here. But yeah, cool. This is too high. Now what we do is we kind of start this process over, right? We say how many times does this green x squared go into? Now we're looking how many times does it go into negative 3x cubed? Well, we know that the coefficient is going to be a negative 3. And there's still kind of one x that we can multiply the x squared by to get that x cubed. So it's just here going to be minus 3x. And you can verify that negative 3x times this green x squared gives us this negative 3x cubed. And now we multiply it out again. So minus 3x cubed. Negative 3x times positive 3x is negative 9x squared. And then negative 3x times 2 is negative 6x. Okay, now we subtract these. And we're just going to keep doing this process. So these cancel, negative 4x squared minus negative 9x squared. So now we're adding 9x squared. So that's positive 5x squared. 5x minus negative 6x is positive 11x. And now we're dropping this one all the way down, or this negative one, right? So minus 1. Okay, let's keep going until we reach our remainder. So now we have to go into x squared into 5x squared. Well, we have enough x's, but we can still multiply our green by 5. So here we'd say positive 5, so plus 5. Multiply it out. That gives us 5x squared plus 15x. And then plus 10 here. Okay. Boom. Subtract these out. These cancel. 11x minus 15x is negative 4x. And negative 1 minus 10 is negative 11. Okay, now we have reached our remainder. One way that we can know this is because there's kind of nothing left to drop down if we were to keep going. Another way is like we cannot multiply anything by x squared to get 4x because 4x has a lower degree than x squared. So once this expression down here has a lower degree, meaning like the exponent on x, than the divisor, that's how we know we're done, and this is the remainder. So we'll say that here is our remainder. Okay, so now we want to write our answer in this format that we talked about earlier. So if we had 36 remainder 4, so we wrote it as 36 plus 4/7. So what we'll do is we first just write this. This we'll call like the quotient, but this is the quotient without the remainder. But so we'll first write that, just like we had 36 here. So our final answer, I'll make this a little bigger, 2x squared minus 3x plus 5. Okay, now the remainder comes in, and I'll use a different color for the remainder. So the remainder is going to be plus. We can always just use a plus here. If there's a negative and you want to convert it to a minus, you can, but using a plus is always going to be safe. So plus, and now we have a fraction bar, because remember, here it's plus 4/7. So on the top is the remainder. Our remainder was negative 4x minus 11. And on the bottom is the divisor here, right? So it was whatever we were dividing by. So x squared plus 3x plus 2. And even though this still looks kind of incomplete because of that whole blue, that part in blue, this is indeed the final answer because there's no way we can simplify this anymore. So here we say this is our final answer. We have our quotient and then we have our remainder as well. So that's the format that we want to write it in. Let's move on right now to synthetic division. So here's another polynomial long division one you can use. But let's talk about synthetic division, which is another one. So polynomial long division, that's the process, right? If we have time, we'll come back and do this one quick, but synthetic division is an easier process, except there's a specific format the division problem needs to be in. And that's that the thing being divided, the divisor, it needs to be x minus a, where that a can be, let's say, can be anything. But this is just to say, like, it can't be anything with a higher degree than just 1. We would say this has a degree of 1. And if it has a higher degree of 1, we cannot use synthetic division. And you'll see why once we kind of see what synthetic division is. So we would say that this is, if this is x minus a, right, then this is, we'd say a equals 3, right? It's not negative 3, it's 3 because it's x minus a. And the way that we want to set synthetic division up is like this. So if you haven't done this before, it might look a little weird at first, but once you get used to it, it's pretty cool. So we draw this kind of like right angle, like half a box pretty much, and we put a in here. So right now I'm going to put 3, right? I'm not putting negative 3 because it was x minus 3. I'm putting positive 3 because it's x minus a. So if it helps to think about it like this, you basically just need to flip the sign of whatever's in here. Cool. So we put the 3 there. Now what we do is to the right of this box thing, we write all the coefficients. So the coefficient here, well, this is negative 1x cubed. It's the same thing as that. So the coefficient is negative 1. We're writing them left to right. So negative 1. The next coefficient is 4. And then the next coefficient, well, we might be tempted to just put a 9 now. However, notice we are once again skipping a term. We don't have a term that is just something times x or a first degree term. And so therefore, we put a 0 in here, just like we did earlier, but we don't need the x part because it's just the coefficient. So the coefficient was 0. And in synthetic division, this is absolutely necessary to like be able to do the problem. Okay, and then after 0x, we have 9. So any terms that are skipped, we replace them with 0. Okay, next we leave some space below all that and then draw a horizontal line just like that. And then here's the process. So It always starts like this. You simply drop the very left number straight down, or not the very left number, but the very left coefficient, right? So not the 3, but the -1 in this case. So drop it straight down and just write that same value, -1. Then what you do, and so this should feel like it has a similar pattern to long division because it kind of does, but it's also like a very optimized and simplified version of it. So now you multiply this -1 times whatever is in that box, which in our case is just 3, so -1 times 3. Then we write that right here in underneath um, that 4. So basically it just always goes to the top right of whatever you multiplied, right? We multiplied the -1, so we go up and to the right and we write a -3. Now what you do is you just combine downward. And when I say combine, I basically just mean add. So this might feel different because in long division you subtract. Here we just add. So it's 4 plus -3, and we write the sum down here. So 4 plus -3, that's +1. Boom. Okay, I'm not going to draw arrows for all these because it's going to get crowded, but now I take this +1 and I do the same thing as I did with the -1. I multiply it by 3. That's 1 times 3, which is 3. And then I'll write that product. I'll use the orange arrows still. And I'll write that up here. It was 3. Okay, now I combine 0 and 3, or I add them. So 0 plus 3 is 3. Now I multiply again 3 times, once again, just that 3. And I write the product up here, which is 3 times 3 is 9. Now these are both 9, which is tempting to think they cancel, but remember we are adding here. So it's 9 plus 9, so it's 18. Okay, and then we're done. And then what you do is, so earlier we kind of stripped the x's away to turn everything just into coefficients. But now what we do is we kind of bring those x's all back. So what this means is, and you can always kind of do this like this backwards, where you know that whoops, you know that this last one, this 18 in this case, it will always be the remainder. So here's our remainder, which means if you kind of go backwards, then the 3 is therefore a constant. So meaning like it doesn't have an x at all. The 1, it would have an x just to the first power, so just an x, and then the -1 would have an x squared. Another way that you can think about this is that if you're dividing x to the something x to the third by something x, well, the first term of the quotient should be x squared because we're taking away just one power of x. So if we want to write this left to right, we now know that this is going to be the x squared term, and everything else will kind of follow after it, decreasing their degree by 1. So it was -1. So let's write our solution here. It's going to be -1, or just negative x squared, -1x squared. Okay, then comes x, and we just have 1, so plus just x. There's no exponent. We don't need to put the 1 there. Plus 3. And then what do we do with the remainder? Well, we put a plus. We make a fraction. So this is the same as what we learned in long division up above. Now we go back to here and we say, well, what were we dividing by? It was x minus 3. So that's what goes on the bottom. And what was the remainder? It was 18. So that's what goes up top. And there we go. And that's our solution to this problem for synthetic division. Okay, that's good. So synthetic division, once you get the hang of it, can come super fast. So let's do it for this one. So x minus 6, that means that a is equal to, this is x minus a. So a is equal to +6. Okay, so that's what we're putting in this box, 6. And then we write down the coefficients. This one, it does not skip any. So we don't have to write any zeros. We have 1, -5, -8, 13, negative 12. Draw our line, and then we go. It can be really fast once you get the hang of it. So drop down the 1, that's 1. 6 times 1, we write that right here, it's 6. Negative 5 plus, all right, the plus is here just to remind us, 6, that's 1 again. 1 times 6 is obviously 6 again. Negative 8 plus 6 is negative 2. Negative 2 times 6 is negative 12. Add these together. 13 plus negative 12 is positive 1. 6, because 6 times 1. Add these, boom, negative 12 plus positive 6. That's going to be negative 6. Finish my arrows there. And we're done. And so now we say, all right, we now know this is remainder. You can always mark it off like this. Negative 6 is the remainder. 1 is x to the 0, meaning there's no x at all. It's just the 1 itself. This one is x to the 1, aka x. This one has to be x squared, and this one has to be x to the third. We've been getting a lot of 1s and negative 1s here, but notice if this was a number other than that, we're writing that as a coefficient. We'll see it here with this too. So 1x to the third, this is just x to the third, positive, so plus x squared, minus, now it's 2, so minus 2x to the 1, or just 2x, plus 1, x to the 0 is 1, so 1 times 1, 1. That's why, we consider this to have a degree of 0 in a way. And then now we write our remainder. Here's where we can use a minus sign if we want. Our remainder is just simply negative 6. So therefore, minus 6 over, well, what we're dividing by, x minus 6. And there's our answer. Make sure I got that right. Yep. All right. Let's do the last part of this unit, which is talking about something called the remainder theorem. So the remainder theorem can be a little bit tricky at first to wrap your head around, but the using it in practice is actually pretty easy. But and you don't really need to understand how it's derived necessarily. So we'll just define it. And if you're interested in how it's derived, you can look that up as well. But here we're just going to define it and we're going to use it to solve some problems. So here we're using some function notation, right? So f of x means that it's the y value for a specific x value. So we're just in general, here we're kind of just saying it's a function, f of x. It's a function of x. And when we divide it by x minus k, so notice earlier we were saying x minus a, k, a, both of those just kind of represent constants. So x minus something. Then the remainder is f of k. Okay, so when we put this in practice, it's going to feel a little bit strange in terms of why this even works in the first place. But what this is saying is that if we can just find the remainder when we divide by x minus k, then we know automatically what the output is for that function when the input is k. So let's look at this example. Use synthetic division to evaluate this function, f of x equals 5x cubed minus x squared plus 13x plus 29, when x is negative 4. So really what they're asking us here is find f of negative 4, right? And we might say, well, that's easy. We just plug in negative 4 for x. And that's true. And that's what you can do to verify this. But these problems are about using the remainder theorem and kind of understanding it. So here we're going to find f of 4 in a different way other than just plugging it into our original function. And that's going to be the remainder theorem. So let's look up here. We have the remainder equals f of k. Okay, cool. So we're looking for f of negative 4. So our k value is negative 4. And then if we look at what this definition is telling us earlier, it's telling us that if you take that same f, that same function, and divide it by x minus k, you can, whatever that remainder is going to tell you f of -4. Okay, so we want to divide by x minus, our k is -4, so x minus -4, aka x plus 4. We need to divide this by x plus 4, basically. Divide this by x plus 4. Well, we know how to divide by a simple like x plus k or x minus a like this with synthetic division. So let's set that up. And now notice, remember, you have to kind of flip this sign. So x minus -4, it's -4 that we have to write in here. Basically, whatever like this is, if you're doing a remainder theorem problem, whatever the x value is the value going in this window right here. Okay, now let's write these out. We're not skipping any terms, so it's 5, -1, 13, and 29. Okay. So drop the 5 down, that's 5, -20 right here. 5 times -4. Combine these to get -21. -4 times -21 is going to give us a positive, and that's 84. Now we combine these to get 97. And then -4 times 97, so you can see this is getting really big. It's going to be a negative, and it's going to be 388. And then -29 combined with -388, and I need to look at my notes for this because I forgot it, it's -359. Boom. And in a problem like this, we're not even curious about the entire quotient. All we care about is the remainder, right? We know that -359 is now our remainder. Okay, so what does that mean? Well, going back up to this, we just found that r is equal to -359. So therefore, f of k, or in our case, f of -4, is also equal to -359. So that's one way to evaluate a function at a specific x value. If it's a polynomial, you can divide it by x minus k, aka just throw that value into synthetic division. So sometimes that's easier than actually evaluating the function itself once you kind of get the hang of it. Especially in this one, like we could verify by plugging in -4 to all these x values, but that's going to be kind of tedious, especially once you do like -4 cubed and all that. You can see the answer is -359. So clearly, like there's a lot of math involved if you want to use the exponents. Here, we found a way to evaluate this without even needing to like use exponents, really. We just use synthetic division. So pretty cool. Let's finish it off on one more. So you might see problems like this that say, use synthetic division to evaluate the function for the indicated value of x. So x equals 6 for this specific function. So we're being asked, what is f of 6? This is one where you might say, that seems easier to just plug in. But you still need to use exponents. So kind of with synthetic division, we know, okay, the 6 goes in there. I can write out my coefficients. 1, notice I need to skip an x squared term, so 0, -6, 1. And I can now evaluate this function super quickly. So 1, 6, 6, 36, 30. 30 times 6 is 180. 180 plus 1 is 181. And there's my answer. It's 181 because that's the remainder when I divide by x minus 6. So there I kind of skipped a lot of the logic, but that's kind of the idea of this remainder theorem, is that it's this very cool proved theorem that you can use to evaluate functions quickly. And once you get the hang of it, you realize kind of what needs to go where. All you're doing is putting that 6 into the window of long division, and then the answer is simply the remainder. So pretty cool. Cool, let's go ahead and wrap it up right there. Emma. I hope you learned something.